Okay, let's break down this problem about the Dirac delta function and a point charge. Here's the problem we are looking at. We are told that a point source or a point charge can actually be represented or identified using a Dirac delta function. The question gives us a specific scenario. If we have a point charge, let's call its value q, located at the position r equals -2, what value do we get from evaluating this integral? The integral is from -infinity to infinity of delta r times qr dr. And we have a few options. A0, BQ evaluated at 2, CQ evaluated at -2, BQ evaluated at 0, or E not attempted. Alright, let's dive into the solution. Our goal is to evaluate this integral. The integral from -infinity to infinity of delta r times qr dr. The very first thing we need to do is figure out how to mathematically represent this function qr, based on the problem statement that says if a point charge q is located at r equals -2. So step 1 is all about defining our function qr. A general way to represent a point charge, let's say its value is capital Q, located at a position r0, is using a charge density function given by qr equals capital Q times delta of r minus r0. Now, in our specific problem, the value of the point charge is q. We'll use capital Q here just to distinguish it from the function qr itself, and it's located at r0 equals -2. The function qr becomes capital Q times delta of r minus -2, which simplifies to capital Q times delta of r plus 2. Step 2 is straightforward. We're going to take this expression for qr that we just found, which is capital Q times delta of r plus 2, and substitute it directly into the integral that we need to evaluate. So our integral becomes the integral from -infinity to infinity of delta r times, in parentheses, capital Q times delta of r plus 2 dr. Now, for step 3, we can see that capital Q is just a constant value representing the magnitude of the charge. And with integrals, we know that any constant factor can be pulled outside the integral sign. So we can factor out the capital Q. And our expression is now capital Q times the integral from -infinity to infinity of delta r times delta of r plus 2 dr. Step 4 is where we evaluate the integral that's left. To do this, we're going to use a fundamental property of the Dirac delta function called the shifting property. This property tells us that the integral from -infinity to infinity of some function fx times delta of x minus a dx is equal to the value of the function f evaluated at a, so f of a. Now let's look at our specific integral. The integral from -infinity to infinity of delta r times delta of r times delta of delta r times delta of r times delta of s. So to do this, to the shifting property formula, we can identify fr as the function delta of r plus 2. The sampling delta function is delta of r, which corresponds to delta of r minus a, where a is equal to 0. So applying the shifting property, this integral, the integral from -infinity to infinity of delta r times delta of r plus 2 dr is equal to our function f evaluated at a, which is delta of 0 plus 2. This simplifies to delta of 0 plus 2. Step 5 is about determining the actual value of delta of 2. The Dirac delta function delta x has a very specific property. It is equal to 0 for any value of x that is not equal to 0. Since the argument in our case is 2 and 2 is definitely not equal to 0, it means that delta of 2 is equal to 0. Finally, for step 6, we calculate the final result by putting everything back together. From step 3, we had capital Q multiplied by the integral from -infinity to infinity of delta r times delta of r plus 2 dr. We just found that this integral evaluates to delta of 2, which is 0. So our final result is capital Q multiplied by 0, which equals 0. The integral evaluates to 0. So to wrap it all up, the result of the integral we needed to evaluate is 0. Looking back at our options, this corresponds to option A. Therefore, the final answer is option A, which is 0.